In the last section here, I want to come back a little bit to the different notions of problems that we've been talking about. When I was explaining the problems in the last section, you may already have seen that sometimes I didn't explain what's on the slide, but I explained the more intuitive optimization version. And so let's pull that straight, because this is something that's often relevant, and there's a few little details to point out to make sure that we can deal with optimization problems in the same way. So far, everything has to be a decision version. A problem was a language, and then something can be in the language or not. Or to say the same thing, you're given an input, and you can say yes or no. It does make sense to also define the more general problems where we try to find the best possible solution. For the hardness theory, we'll stick with the decision versions. But there's an easy way to put the problems into context and connect them. And that's what I want to do in this part. So formally, an optimization problem has a bunch of different components. There's an input alphabet. We somehow have to encode the input again. But this time we also produce an output. So we also have to say how that looks like. Then there's a certain language over this input alphabet of allowable instances. So these are valid encodings of some problem. Again, if we want to make this more concrete, say we look at TSP as our running example again, then the allowable instances would be distance matrices. And the input alphabet would be some way to encode the distance matrices. Maybe it's just a binary alphabet and we write down the numbers in binary. Maybe we allow a third symbol to say this is the end of one number and the beginning of the next. It makes it a bit easier to read. Then maybe not all of these instances are really relevant for this problem. I guess for TSP, the two would be the same, but maybe you want to restrict TSP to a certain variant. To make this clear here, let me say it's metric TSP, where the distances have to satisfy the triangle inequality. So it has to be, when you go, metric means if you have cities here, A, B, C, and you go from A to B, that cannot take you longer than going from A to C and then to B. So the distance from A to B should be at most the distance to go via C, the detour. Okay? This is a very natural condition, but if you just specify a matrix of numbers, this is not guaranteed, right? It may not be satisfied. I didn't want to zoom. Okay, so in general this may be violated, but let's suppose we look at metric TSP where we only allow instances that satisfy this. So the actual problem instances would be metric distance matrices. And again, some encoding thereof. And now you already see we need some way of checking that something is an actual instance. Then we have this function n that tells us what are possible solutions for a given instance. And these have to be defined for all of the allowable instances. So for TSP, this would be all possible round trips, so permutations of the cities. Okay. And then we have a cost function, which given some allowable problem instance and a solution, where this is one of the possible solutions, tells us what's the cost of this. And I keep the terminology neutral because we can use the same for minimizing and maximization. Now, cost sounds like you want to minimize, but well, depends whose cost, I guess. The important bit is this has to be a function that's computable. We'll come to that. So this is, so far, this is a general definition for any kind of optimization problem. There's no mention at this point about efficiency and how fast we can do things, okay? Okay, in general, this cost function can be any real number. Now, good luck with representing exact real numbers on your Turing machine, so probably it will be rational or maybe even an integer. Okay, and the goal is minimization or maximization. Is that clear so far? Now, in general, this is a very broad definition. What does it mean to solve such a problem? We're given such an optimization problem, then we say that a solution, some y in the solution set for x is optimal if the cost of this specific y minimizes or maximizes, depending on the problem, right? Goal is this part of the input. Minimizes or maximizes the cost among all possible solutions for this instance. That's the very natural definition, okay? An optimal solution is one that minimizes cost if you're minimizing and maximizes reward if you're maximizing. Okay, we'll always deal with consistent algorithms. An algorithm is consistent with an optimization problem if it always outputs something that is an allowable solution for this instance. Again, in principle, if you specify an arbitrary program, it might do whatever nonsense. We're not usually interested in this. So consistent means it has to be in this set of possible solutions. But the important bit is an algorithm solves this optimization problem if it's consistent and it all outputs the optimal solution for all instances. Okay? And here, let me stress again, we're only requiring this for the actual instances. Okay. We've seen many examples in the list previously where we had a threshold, usually called k. And if you say, I'm not giving you this threshold, but I'm asking for the best possible solution, then you naturally get an optimization problem for many of the problems we've seen before. And we can very briefly run through back. Closest string, you can ask what's the smallest k so that you can find a string satisfying this. Max cut, you optimize for the many number of edges. Here you want to maximize. Exact cover is different. There's not really a question of maximization. Maybe you can ask for the fewest elements, but this problem remains hard if it's as is. TSP, of course, you can minimize the cost of the Tor. You can minimize the number of colors you need for graph coloring, minimize the number of sets in set cover, or minimize the cost. Dominating set. So most problems are actually like this, that they're optimization problems. Hamiltonian cycle is an exception, and exact cover is an exception. All the others are optimization problems naturally. Here's a somewhat less immediate example, but one that will also come back at some point. The maximum satisfiability problem. It's a bit awkward, but it has technical reasons why it's useful to look at. So let me introduce it here. We're given a CNF formula, so conjunctive normal form. This popped up earlier, but I skipped over that part, so let me say it again here. It's a Boolean formula, so something comprised of variables and or not conjunctions. But it has a specific form here it's one big AND of different parts, and then each of these clauses, each CI is some xi or not xj or xk and so on. You remember 3sat was exactly 3 of these variables or literals. If we just say C and F, it's unrestricted. And the total number of variables is n. Now maxsat asks to satisfy as many of the clauses as possible. Normal satisfiability means all need to be satisfied because we take the AND. But here we're asking just to satisfy as many as possible. So formally, this would be the allowable and actual instances are all the encodings of such formulas, maybe listing the clauses in some form. Then solutions are assignments of all the variables. So you can write them down as 0 or 1 strings, where the ith position gives you the value of the ith variable. And then the cost of a combination of an input and a solution is the number of clauses that are satisfied. Here's really a reward, not a cost, right? Because we maximize. Okay, is the problem clear? As a Boolean formula, this is a bit nonsensical. Like either the formula is true or not. It doesn't help to satisfy all but one clauses. But let's pretend it's still useful, and it will come up as a reduction partner later. Yep.
This is in conjective normal form, and we are finding next set, and everything is an and. How can others not be true?
Yeah, that's what I said. As a Boolean formula, it doesn't make sense. But you can still define, I want to satisfy at least as many of the clauses. Again, it's a bit of an artificial problem. But it turns out it has, forget about the meaning of the formula. Maybe it's just different conditions, and you'd like to at least meet as many of them. If it's not possible to satisfy everyone, you want to make as many people happy as possible. But it's a bit unnatural, but turns out to be a useful intermediate problem. Okay, so far optimization problems were very general. Now let's try to pin down the efficiency. Do we have NP first? Yeah. Okay, so the first restriction is the equivalent of NP, and NPO is the equivalent optimization problems class. So these are optimization problems where, first of all, I can efficiently decide whether an instance is one that I'm actually interested in. So these were the actual instances. If you give me something, I can't even efficiently tell whether I'm supposed to solve it, it's a bit pointless. So formally, this is in P. And second, there must be an efficient way to decide whether something is a solution. So there's some polynomial, and for every allowable instance and for every possible solution, first of all, the solution shouldn't be too big. If I were asked to produce solutions that are exponentially long, there's no way I'm going to do that efficiently. And secondly, there should be an algorithm that decides for all short enough strings whether or not that is a valid solution. That's also just a sanity check, really. So if someone claims here's a TSP input and here's a round trip, you should at least be able to check whether the round trip is a correct permutation of the cities. Otherwise, we're completely lost. But these are still very weak requirements. And the last one is also important. The cost has to be efficient to be computed. So again, polynomial time. Also very natural. If I can't, given some input, tell you how costly it is, how am I supposed to optimize for it? Okay, so these are all very weak requirements. And that's all for a problem to be an NPO. In particular, it tells you nothing about how to find the solution. but that's the same for problems in NP. The problems where we have a chance to solve them is this class PO. So here it's everything that NPO requires, all of these three, plus there should be an algorithm that in polynomial time computes an optimal solution. Okay, and then together with these, I can also verify that it's indeed optimal if I'm asked to. I think most of the definitions is very natural, is what you would think. NPO is all the problems where I can at least verify that the solution is correct if you give me the solution already. And PO is the ones where I can find it efficiently without being requiring your help to start. So it's not very surprising how these things are formalized, but I think it's worth doing. So that, for example, you don't forget that the cost has to be efficiently evaluable and so on. It's easy sometimes to write down a problem that sounds enticing to solve, but there's not even in NPO because you can't even compute the cost, for example. Okay. At this point, I think it's worth recapping the different types of problems we had. Specifically because we had the Turing machines with their languages and NP in the original definition, but then also this VP definition. And now we have optimization problems. So I would organize this as what is the output? Either we just do a single value, yes or no, or we have to provide a solution or a certificate. And the other axis is whether we're checking a given threshold or whether we have to find the optimal value. And so what we've just defined would be the bottom right. These are optimization problems. I'm given nothing, but I'm supposed to find the optimal value myself and also provide a certificate, a solution alongside with it. Right? Now, the other extreme was the decision problems. This is where we started. That's the same as languages. So here we're just given a string and we asked yes, no. Now we've also had this corner below here, which is sometimes called the search problem. So this is effectively what we wanted for VP. I'm still asking a yes/no question, but instead of, VP requires this as input. Instead of just claiming yes/no, I'm supposed to prove that my answer is correct. And so you could say this is the problem in satisfiability. I'm asked a yes/no question: is the formula satisfiable? And then the decision problem, I said yes, and you were happy with that. Now in the search problem, I say yes, and then you ask me, okay, fine, what's the satisfying assignment? Okay. And this corresponds to the optimization problem, how we defined it on the previous slides, where I'm also supposed to provide you with the concrete answer. And then the last bit also sometimes makes sense to talk about. And that's often then called the evaluation problem. That's an optimization problem. You're not actually interested in finding the optimal solution itself. You're just asking for the threshold. What's the best possible cost that you can achieve? but I don't have to provide you a proof. I don't have to provide you the solution itself. Okay. And so the reason why I'm drawing this matrix is that you can go from one collection of problems to the other. And some directions are easy. For example, you can always go this direction essentially by using that the cost function is efficiently computable, and otherwise by essentially forgetting the certificate. Right? That's easy. If you can solve one of the bottom row, you can solve the top row by just not outputting the certificate. The interesting question is whether you can go top down. The other thing you can also do very easily is this direction. Otherwise, it's easy. Right, if I'm given a threshold and I can find the optimal value, I just check the optimal value against the threshold and output whether it's better or not. The interesting bits are, can I go from left to right? And then you can basically always do a binary search for the right cutoff point. So you can use as a black box that you can decide whether something is above or below the threshold. You can use a binary search on the numbers that make up the cost function to at least get us as close to the optimal value as possible. And if the cost function is efficiently computable, it can't be an arbitrary real number. So you'll have to converge eventually. It's also true because the number of possible solutions is not arbitrary. They have to be bounded in size, right? So this works, and even though the search space is very big, is exponential, you're taking binary search, you're taking the log of the search space. So that's back to polynomial. So that's actually a general reduction, specifically if the costs are discrete. Now, an interesting question is whether you can go from top down, from thresholds, from the single value, from decision to search. And in general, it seems this is not always possible. But for any concrete problem you look at, it seems usually easy. So you look at this on the tutorial sheet. But most of the time you can do it. So if you put this together, by and large, all four corners are not as far away from each other. For most problems, the complexity of those four corners is the same in terms of polynomial versus exponential. Okay. Questions on this terminology? Is that clear? There's even some, depending on who teaches undergraduate modules, sometimes people work everything from search problems. I don't know if anyone has experienced that. It's not so commonly done. Okay. A few of these things, there's a few definitions that formalize some of what I've just said. I'll go over those a bit more quickly. So if we have an optimization problem in the way we've defined it before, then Let's denote, this is, I guess, in general, so worth pointing out. I'll write opt subscript the problem and then an input, so an instance x, for the value of the optimal cost. Then we can define threshold languages, which is turning an optimization problem into a decision problem by using pairs of an input and a value, a threshold. And then you include in the language all the pairs where the optimal value is better than the thresholds. And you have these two distinctions for min and max. The only thing here worth pointing out, k subscript 2, this is supposed to mean the string k is a binary string. And so I'm just reading this as a binary number. Okay. I think here I'm assuming that the cost is an integer to make life a bit easier. So is it clear what the threshold language is? You take an optimization problem and you turn it into the threshold language by taking all the pairs of instances and the threshold where the optimal value is better than the threshold. Okay. We say such an optimization problem now is NP-hard when this threshold language is NP-hard. Formally, we have only defined NP-hardness for languages. That's why we need this definition to lift it to optimization problems. And it's not hard to prove that then if you have an optimization problem, which is the other way around, if the threshold language is NP-hard and we assume, as usual, P is not equals NP, then the optimization problem cannot be efficiently solvable. Okay? Intuitive statement, I guess. But let's briefly spell out the proof. We prove this by contraposition, so assume that U would be efficiently solvable. Then we have a polynomial time algorithm that computes the optimal solution in all cases for all instances, right? In particular, we can compute the optimal value of that solution because cost is computable. And that means we can decide whether the optimal value is better than any threshold in polynomial time. So we've decided whether the language, whether an element is in the language. That means the threshold language is in P. But if the language is NP-hard and is in P, that means P equals NP, which is a contradiction to our assumption. That's what we had this one for all for one lemma and earlier in this unit. So that means lang U cannot be NP-hard. That's a contradiction, so U cannot have been in PO. Okay? So it just means that if the threshold language is NP-hard, the optimization problem will not be efficiently solvable. It's one of the easy directions in the table. And as a concrete example, we can show that this max SAT problem is NP-hard. And also here, formally, we can do a reduction to the threshold problem. So just to spell that out once, we take the 3-SAT problem, a known NP-hard problem that we've worked on before, NP-complete problem, and we reduce it to this threshold language for max SAT. And this is actually very easy because it's kind of a special case of max SAT if you look at it. So given any 3-SAT instance X, and suppose it has m clauses, then we just produce this pair X, M, which means, can I satisfy all clauses in my formula? That's exactly satisfiability. So the rest is kind of just this chain of equivalences. X is a 3-SAT, is a yes instance, if and only if it's satisfiable, which means all of its clauses, m clauses, are satisfiable. That means XM is in the threshold language. Okay. That's a tiny and very simple example of how you can use this definition to prove that optimization problems are NP-hard. So that we can talk about those being NP-hard, not just the threshold languages or decision problems. That's an alternative. Most of the time we'll be happy with just proving that the decision version is hard and that the optimization version is then even harder, is kind of proven once for all. Okay, let's wrap up this intro section. Much of this supposedly is covered in some undergrad TCS modules. Maybe not in the same kind of form of setup. So we formalized what it means to have a polytime algorithm, which we call efficient. We've looked at decision problems and these other forms of problems, Turing machines as a way to compute things, and we showed how we can establish this theory of intractability. So we can now rigorously prove that some problems are NP-hard, which means they probably don't have a solution. But we set out to kind of solve problems despite this fact, right? This was all a prelude to what do we do now? And so let's get started with that part.